Hi, students. Today we're going to be talking about experimental and theoretical probability. I'm going to go through these notes pretty quickly. You are allowed to use a calculator if you have one. Make sure that you've printed off the notes beforehand to make this a lot easier. All right, experimental probability is the ratio of the number of times an event occurs to the total number of trials. Experimental probability is what does happen, what happens in your experiment. Theoretical probability is the probability of an event happening based on the possible outcomes. So, what should happen in theory? So, if you're flipping a coin, you have two chances, two possible landings, heads or tails. So theoretical probability means if it lands on heads the first time you flip the coin, then it should land on tails the second time. But if you actually conduct your experiment, you might realize that that doesn't happen exactly the way it should happen in theory. So we're going to just practice some probabilities here. Number one, using the spinner below to answer the questions. Use the spinner below to answer the questions. Then spin the spinner 10 times and then complete the table. So we're going to just answer these questions based on the spinner here, and then I will do the second part for you. So, what is the theoretical probability of spinning a section with stripes? So you always have to go through and count how many different sections you have. 1, 2, 3, 4, 5, 6, 7, 8 sections. All right, so the probability of getting, oopsies, there we go, probability of getting stripes. This is how we would write out what we're doing. Would be, I only see one with stripes, so it's 1 out of 8 total. What is the theoretical probability of spinning a section with stars? So probability of getting a section with stars would be 2 out of 8, which simplifies to 1 out of 4. Make sure you always simplify those fractions or else it doesn't count. What's the theoretical probability of not spinning a solid or striped? So not solid, not the striped. So what is remaining? The remaining is the stars or the dots. That's 3 out of 8 chances. All right. So next what I'm going to do is I'm actually going to conduct the experiment. It said that we're going to spin the spinner 10 times. So let's see if I can spin this spinner up here. So I'm going to do one spin. And as it goes, it's got stripes on the first try. I'm going to tally mark what it gives me. All right. My second spin is a white space. Third spin, another white space. Fourth spin, ooh, stripes. Fifth spin, a star. Sixth spin, oopsies, there we go. I got another white space. Seventh spin, a white space. Eighth spin, white space. 10th spin, a star. All right, and then it's always good to double check. I've got 5, 6, 7, 8, 9. Whoopsies, looks like I miscounted. So I'm just going to do one more. Does that look like white? Let's just say it fell on white. Okay. Sometimes, this is an experiment. We all know that we're human. Sometimes we make errors in whatever we're doing. Either I miscounted or I forgot to write a tally somewhere, and it is all good. Okay. It's just an experiment here. So I recount 5, 6, 7, 8, 9, 10. Good. That's over here on the total number of spins. That's where we're going to record our tallies. And again, double check that you did your experiment 10 times. And for this, you guys just watched me do it 10 times. And now we're just going to list our experimental probability. So I had a total of 10. And for stripes, I spun it. It landed on stripes 2 out of the 10 times. So that is 1/5 of the time. For white space, 6 out of 10 times, which is 3 out of the 5. 0 out of 10 times, which would be 0. And for stars, 2 out of 10 times, which is 1/5. Again, you want to count up your fractions on the side just to make sure all of your fractions add up to one whole. So I'm taking into account all of the spins that that occurred in my experiment. So basically, if we think about the theory here, in theory, how many times should I have landed on the stripes, for example? Well, remember, there's 8 different slices of my circle, and there's only one option for stripes. So I should have landed on stripes 1 out of 8 of the spins. So this is in theory, theoretical probability. White, there is 4 out of the 8 slices, which is half. Okay, let me rewrite that. 4 out of 8, which is half. And I've got dots. Dots was also 1/8 in theory, and stars. Stars was 2 out of the 8 slices, which is 1/4 of the time. All right, so looking at our information, comparing the experimental probability to the theoretical probability, do any of them match? Are any of them the exact same amount? Well, the answer here is no. There's many reasons to that. First of all, my trials, I did 10 trials, and when I'm simplifying my fraction out of 10, it doesn't necessarily match my fractions out of 8 with a denominator of 8. So that's one example. But secondly, the number of trials is actually really low. Doing something 10 times is not a lot. So the more trials you have, the closer you'll get to your theoretical probability. If you only try something a few times in your experiment, then you don't get great results. All right, we're going to look at the next page of your notes. We've got Scott. He's also spinning a spinner. You'll notice that the spinner has 4 equal sections, a red, a yellow, a blue, and a green. I want you to fill out this chart, pause the video. You're going to record experimental probability versus theoretical probability. All right, so he has, if he is spinning the spinner 40 times, he gets red 15 out of those 40 times. That simplifies to 3/8. And again, you can use a calculator here if you need it. Yellow was 10 out of 40, 1/4. Green was 10 out of 40, 1/4. Blue was 5 out of 40. That's 1/8. In theory, he should be getting red 1/4 of the time, yellow 1/4 of the time, green 1/4 of the time, and blue 1/4 of the time. This is because that color occurs one time out of 4 different slices of our circle, right? So if I landed on blue, there's only one option for blue out of a total of 4 options here, 4 slices of our circle. So when looking at our results here, Scott spun it 40 times. He actually matches his experimental probability to his theoretical probability twice. So the more times he spun his spinner, the closer his values got to theoretical probability. Now we're going to talk about something called relative frequency. Relative frequency is the total number of successful attempts divided by the total number of trials. It's going to be used to make predictions. We're going to write this as a percentage. Okay? As the number of trials increases, the relative frequency of an event will approach that theoretical probability. So what we're going to do is look at the chart below. It says the spinner at the right is spun 50 times, and the results are shown in the table below. So again, it's important to know that this happened 50 times. So we are going to take a look. A 1 was spun or landed on 12 out of the 50 times. When I record that as a relative frequency, I would originally put 12 out of 50, but it simplifies to 6 out of 25. And then when I divide 6 divided by 25 in my calculator, I get 24%. That's how we go from a fraction to a percentage using our calculator. The fraction bar literally means divide. So we're going to go through and figure out the rest of the relative frequencies here. Remember, your total is 50. So we landed on a 2, 8 out of 50 times, which simplifies to 4/25, which is 16%. 13/50 in the calculator is 26%. 10/50 is 1/5, which is 20%. And 7/50 is 14%. So this is just our experiment of spinning the spinner 50 times. Here's our results. Here's how we use our results to change it into a relative frequency. The benefit of seeing it as a percentage is because it's hard to compare fractions when they have different denominators. So when you see different denominators here, it makes it more challenging for your brain to process what's happening. But if we see all of these numbers, that's a much better way of visualizing the results of our experiment. We could say in this experiment, the number 3 was spun the most. So if I was to spin one more time, I have a better chance of spinning a 3 based on my past results. Maybe it's just the way the spinner is spun. Maybe it's the flick of this guy's wrist. Who knows? But you can use this percentage to help you make predictions in the future. All right. So on the next part of your chart, it's saying, now spin the spinner 100 times. Well, we've done that for you. We've got blue happened 21 times. So write this down if you've printed off your notes. 2 was spun 20 times. 3 was spun 19 times. 4 was spun 18 times. 5 was spun 22 times. As you see, the more times we spin, the closer we get to our theoretical probability. Let's go ahead and calculate our relative frequencies. Since the total was 100 times, I'm just dividing my number of spins for 1 by 100, and I get 21%. So that means the next one's 20%, 19%, 18%, 22%. Make sure you have all this written down. So the next question says, what do you notice about these results after the spinner was spun 100 times? And I think I alluded to that answer. The relative frequencies are either at or close to 20%. 20% is 1/5 written as a fraction. And at each of these results over here on our spinner, in theory, all had a 1 out of 5 chances of being landed on after the spin. So again, the more times or the more trials you have for an experiment, the closer you get to the theoretical probability. So I just answered this question for you. What are the theoretical probabilities of spinning each of these numbers? Well, they all had an equal chance of being landed on, and there was 5 sections. So 1 out of 5, which is 20%. The probability of landing on a 6, well, there wasn't a 6, so that would be a 0% probability of landing on a 6 because there wasn't a 6 there and that just won't happen. All right, last but not least, how does the relative frequency change between when the spinner is spun 50 times versus 100 times? Again, as the number of trials increase, the experimental probability gets closer to the theoretical probability. We used relative frequency here to help us understand that better. All right, looks like we're done. Make sure that you do your practice and your exit ticket for today.